So you guys did the rewind at your boards, and I just want to go over a couple of them so that you have the answers to them. I know that you guys have an answer key, but I just want to review a couple of them. So number 1 says triangle SRT is congruent to triangle LMN. SR is equal to 7B plus 8, and LM is equal to 11B minus 12. So how would we find B and SR? Well, since SR and LM are in corresponding spots in those triangles, and you know that because they're in the same spot in the name of the triangle, you can say that SR is congruent to LM. So I would say 7B plus 8 is equal to 11B minus 12. And then to solve that, you would just isolate B. So I'm going to subtract 7B from this side and I end up with 4B. And then I'm going to add 12 to this side and I'm going to get 20. So then you know that B ends up being 5. And then to find SR, we just plug that in. So if I plug that into this over here, I get 7 times 5, which is 35, plus 8, which is 43. So SR is 43. Given that polygon ABCD is congruent to polygon EFGH, identify the corresponding part for CD. So I take a look at this and I say CD is the last 2 letters here. So in this quadrilateral, it would have to be GH. So GH would be the segment that corresponds to the segment CD. All right, in number 3, we had a 2-column proof. So I know that 2-column proofs can be a huge challenge, but the best way to work on them is to practice them. So you're going to keep seeing them show up over and over and over again. So I'm going to go ahead and write this one out so that you guys have it. So go ahead and write this down on your slides if you didn't get it during the rewind. So let me move the page down a little bit. The first thing you should always do with a 2-column proof is write out your givens. So my given is Q is the midpoint. I'm going to abbreviate that MP of LN and MP. Angle L is congruent to angle P. It's also a given. And then my last given is LM is congruent to NP. All right, I am trying to prove this right here, that LMQ is congruent to NPQ. And like we talked about before your quiz, to prove that a triangle is congruent, you need to prove that all the angles and all the sides are congruent. So let's take a look at the information that we have right now before we figure out where we're going to go with this. So I know angle L is congruent to angle P. All right, is there anything else I can say about any other angles? Hopefully you're looking at this and seeing that these right here are vertical angles. So we could say that LQM, that angle LQM, is congruent to this angle PQN. And remember that Q always needs to be in the middle because Q is the vertex, okay? And those are vertical angles, so our justification is we just say vertical angles. Now that I know that those 2 angles are congruent, that Q right here has a set of vertical angles, and I also knew already that P and L were congruent angles, what can I say about M and N? I can say that angle M is congruent to angle N based on the third angle theorem. And remember that the third angle theorem says if 2 of the angles are already congruent, the third one has to be congruent because triangles always add up to 180 degrees. So if you already know 2 of them, you can figure out that the third one is congruent. So now we've got all the angles are congruent. I'm going to erase this circle just so it doesn't get in the way. All right, I know that all the angles are congruent, so I'm done with that. Now I need to figure out the sides. Well, I already have LM and PNP or PN. So I just need the other sides. My first given is that Q is the midpoint. What does it mean for something to be a midpoint? Hopefully you're thinking it means it's in the middle. If Q is the midpoint of LN, that means that it takes LN and cuts it in half. So if Q is right in the middle, then what could you say about LQ and QN? You could say that LQ is congruent to QN. And that would be because definition of midpoint. And again, I'm going to abbreviate that MP. All right, now you also know that Q is the midpoint of MP. So that means that if Q is the midpoint of MP, that what does it do to MQ and PQ? Well, it must also cut those in two equal pieces. So we can say PQ is congruent to MQ. And that would also be definition of midpoint. Now we have all the sides and all the angles, so I'm finally done. So finally, down here in step 8, I can say what I wanted to prove from the beginning, which is triangle LMQ is congruent to NPQ. And I can say that based on definition of congruent triangles, because all three sides and all three angles were congruent. So I know that they're congruent. But I can't see you guys right now, but I'm assuming your eyes are glazing over because that is a lot of work. That is a really long proof. So your proof took 8 steps there to prove that those triangles are congruent. Wouldn't it be awesome if we had a way to prove it with not that many steps? So if there were a way that I could prove that those triangles were congruent to each other without using 8 steps. And the good news is there is. So we're going to start talking now about 5 different properties of triangles that we can use to prove that triangles are congruent that won't take this many steps. And we're going to talk about the first 2 today. So we are talking today about SSS and SAS, and you're going to get used to these abbreviations, but what those stand for is side, 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 and side, angle, side. So we need all 3 sides and all 3 angles to prove that a triangle is congruent, or so we thought in the past. So we thought before that we needed all 3 sides and all 3 angles to prove the triangles are congruent. It turns out we don't. And one of the ways that we can prove a triangle is congruent is by side, 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 which means if I prove that all 3 of the sides are congruent, because that stands for side, 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 then I know the triangle must be congruent. So if all 3 sides are congruent, I know that the triangle must be congruent. Therefore, if I give you BA is congruent to ED, BC is congruent to EF, and AC is congruent to DF, then that would be enough information to prove that the triangles were congruent. So this is just another picture of exactly what we just wrote. And this is the postulate right at the top. Side, side, side congruence. If 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. And just as a quick aside, it is not enough to have 2 sides of a triangle being congruent. You can't assume the third one, because take a look at this. Let's say I have this triangle right here. Let's say in this triangle, this is 1 and this is 2. And let's say in this triangle down here, this is 1 and this is 2. Down here, the other side could be 3, whereas here, this is an isosceles triangle, so the other side would be 2. So just because 2 of the sides are the same, just because you've got 1 and 2 and 1 and 2, that does not mean that the third side has to be the same. So you need all 3 sides, which is why the postulate is SSS. You need all 3 of those sides. So take a look at this proof right here. This question says use SSS to explain why PQR is congruent to PSR. So the first things I want to do, as always with the 2-column proof, are to write down my givens. And I don't have a list of givens here. I just have a figure with some dashes on it. But what do those dashes tell me? What do these dashes tell me about QP and PS? QP must be congruent to PS. That's a given because they drew that in there with those dashes. Same thing with QR and SR. So QR must be congruent to SR. The last thing we need is this other side. What's the other side of this triangle? Take a look at this top triangle, PQR. The other side that we're missing is PR. Take a look at this bottom triangle, PSR. The other side that we're missing there is also PR. So I need to say that PR is congruent to PR because it's part of both of those triangles. So PR is a shared side. It's part of both of those triangles. And to prove that that's congruent, I use the reflexive property. So remember that the reflexive property is the property that lets you say something is equal or congruent to itself. So PR is congruent to itself by the reflexive property. Once you know that, then you're done. So PQR is congruent to PSR based on, and we would put SSS here. So based on side, 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 because we've proven that all three sides are congruent. So that was done in 4 steps. Take a look back at that first problem in the rewind, which we did in 8 steps. If we used side, 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 we could have eliminated all of the steps about angles and just used the steps about sides. We could have been done with this problem right here in probably about 4 steps, instead of having to use all 8 steps. So side, side, side is going to shorten your 2-column proofs by a lot. The other postulate that we're talking about today is SAS, which stands for side, angle, side. And here's the big key with this. So the big key is that you need 2 sides and an angle, but that angle has to be the included angle. So take a look at these pictures right here. Take a look at this first triangle, triangle 1 right here, and take a look at this second triangle right here. I have the blue lines AB and EF, which are congruent, and I have the green lines AC and DE, which are congruent. So I have that, I already know that. And then I also have an angle. And the angle is the included angle, which means it is the angle that connects those 2 sides. All right, so if I want to use side, angle, side, which you will use all the time, you will use 2 sides and 1 angle, that angle has to be in between the 2 sides. So it has to be in between here. So for example, if I drew this triangle, QRS, and I was looking at this side QR and this side RS, what would be the included angle? The included angle would be R, because R is the one that's in between this side and this side. Let's say I have this triangle, DEF, and let's say I say DE is congruent to RS, and QR is congruent to EF, but I gave you this angle down here, angle F. Would that work to prove that these 2 triangles are congruent? No, because F right here is not the included angle. Which would be the included angle? You would need angle E. You would have to get angle E. All right, so side, angle, side, to use this postulate, you need 2 sides and an angle, but the angle has to be in between the 2 sides. So when you go to draw those 2 sides, you should be drawing that angle. So when I went to draw this side, QR and RS, that's the angle that I'm drawing right here. That's the included angle. So take a look at these right here. Would this be enough to prove that ABC and DEF were congruent? I have 2 sides. I have ED is congruent to CB, which we can see because of our 2 dashes. And I've got EF is congruent to AC, which I know because of my 3 dashes. And I've got this angle C is congruent to this angle D. Is that enough to use SAS? So can I use SAS? And the answer is no. Why not? Because in this triangle, angle D is not the included angle. What is the included angle here? The included angle would be angle E. So it would have to be angle E. So no, you could not use SAS here. All right, go ahead and do these 4 problems at your boards. State if the 2 triangles are congruent, and if they are, tell if you know that because of SSS or SAS. So SSS or SAS. Okay, so in number 1, remember that this shared side right here means that this side is congruent. So if this side is congruent, then here I've got this side, and the included angle in both. So yes, these are congruent based on SAS. In number 2, I've got this shared side, and I've got this side and this side. Up top, I've got an included angle. But here in the bottom triangle, I don't have the included angle. I would need this one over here. And I don't have that, so no, I cannot say that those are congruent. In number 3, I've got the shared side, this side up here, and this side down here, and the included angle in both, which means yes, they are congruent, and I use that SAS postulate to prove that. Down here in number 6, here's a shared side, so I know that's congruent, and then I've got another congruent side here, and another congruent side here, which means yes, these are congruent using SSS. As you can see, it's huge, huge, huge to remember that shared sides are always congruent. So every one of these examples had a shared side. So right here in number 1, right here in number 2, in number 3, and in number 4. So reflexive property is going to be a huge one that you're going to use all the time. All right, so let's take a look at how we can verify triangle congruence. So in this problem right here, we've got the triangle UVW on the left, and we've got triangle YX, this should be a Z, YXZ on the right. And the problem tells us that X is equal to 3. And so what we're going to have to do is what? Hopefully you're thinking, yeah, we have to plug in 3 for the X's down here to confirm that it's a congruent triangle. So I know that in UVW, I know that the legs are 2, 3, and 4. So over here in XYZ, I just want to plug in 3, and here it would be 3 times 3 minus 5. What's 3 times 3? 9 minus 5 is 4. So we've got one side is 4. Over here I plug in X, and I just know that that's 3. And then here I plug in X, and that's equal to 2. So in this triangle, the side lengths are 3, 2, and 4, which are the same as the ones in the triangle on the left. So I can say that, yes, these are congruent using side, side, side. So we verified that those were congruent. All right, if I want to prove that triangles are congruent using these, then again, I'm going to ultimately always want to use these in a 2-column proof. So this should really shorten the 2-column proof that we're going to do, because I can either use SSS or SAS. I don't have to prove all 3 angles and all 3 sides. So the first thing I want to do is still write down my givens. So I've got my 2 givens here. L is parallel to M, and EG is congruent to HF. So when I look at this, the first thing that I think whenever I see parallel lines, and I told you guys this last class, but I want to reiterate it again. Whenever you see that lines are parallel, you're probably going to want to use that to prove that angles are congruent using what? Hopefully somebody is saying alternate interior angles. So alternate interior angles. Remember that if these 2 lines are parallel, then this right here, or any line, is a transversal. Any line that touches both of them is a transversal. So that means that there are angles that are alternate interior. So remember, interior means inside, so be in between the parallel lines, and alternate means opposite sides of the transversal. So which angles can I prove are congruent here? I could prove that EGF right here is congruent to GFH based on alternate interior angles. I can prove that EGF is congruent to GFH based on alternate interior angles. I also know that EG is already congruent to FH. And then the last thing I want to do is I'm going to erase the stuff I drew on here. And what's the other thing I said you should always look for? Should always look for a shared side. So if I'm looking at triangle EGF right here, and I'm looking at triangle HFG right here, do they have a shared side? Yes, they share GF. So I can say GF is congruent to GF based on reflexive property. And now that I have that, I've got this angle, I've got this side, and I've got that other side. Is this the included angle right here? Yes, those are the included angles, so that's enough. So I'm done at step 5. I can write my proof now. So triangle EGF is congruent to HFG based on side, angle, side. Because I had 2 sides and the included angle, so that's enough. Okay, so at your seats, I'd like you to go ahead and do your exit ticket. So try your exit ticket here. For number 1, you need to do a 2-column proof, and for number 4, it should be a 2-column proof. Number 3, you do not need a 2-column proof. Number 3, you're just going to go ahead and try plugging in that number 4, or that t equals 4 to verify that. This says 2t squared, and this says 3t plus 1, and this says 4t minus 3, and this says 32, just in case those are a little bit hard to read. So